Hello everyone. In this video I'm going to cover section 3.5 of your book, which is called the PN junction with an applied voltage. We're going to learn what happens when you apply forward bias and when you apply reverse bias, and we're going to learn what those are. This is just going to focus on the qualitative description of the junction operation. If you guys want to learn more about how the current voltage relationship is derived, please go ahead and look at section 3.5.2. So let's review. Here in this image, we have a PN junction. We have that a depletion region was created right here. And then there is an electric field associated with it and a built-in voltage VO. I'm going to talk about the case when ND is equal to NA, so both concentrations are the same just to keep it easier. And we know that this junction is an open circuit and it's in equilibrium, so the diffusion current is going to be equal to the drift current. So now let's going to talk about what happened when reverse bias is applied. So what is reverse bias? Reverse bias is when the positive terminal of your voltage source is applied to the N side of the PN junction and the negative terminal is applied to the P side of the PN junction. So now let's see what happens, and let's look at it from the lattice point of view. So let's start with the N side. So I'm gonna have a phosphorus atom here, and we know that that phosphorus atom has an extra electron. So we have electrons here that are majority carriers. We have those majority carriers there. Those guys, as you can see, are going to be attracted to the positive terminal there. So what happens here on the lattice? If this electron is attracted to the positive terminal, that's going to leave behind a positive bound charge. So that is going to increase the width of your junction here on the N side. So I'm going to draw that. And you end up with this. So what's going to happen on the P side? On the P side, let's look at the lattice. Instead of having this phosphorus atom, we know that we can have a boron atom, and that boron atom has a hole associated with it. So holes are the majority carriers here on the P side. And these holes are going to get attracted to the negative terminal of the voltage source. So what does that mean here on the lattice? You have this hole that's attracted to the negative terminal, so it goes away and leaves behind a negatively charged bottom atom. This is a bound charge that the more you have, the wider the P side of the junction is. So we're going to have a wider junction here. So what does that mean in terms of current? Let's see. So let's look at the majority carriers here. These holes, before they wanted to diffuse, or they still want to diffuse from the highly doped side to the lightly doped side. But they're facing a barrier, they're facing a bigger electric field due to this depletion region. So the diffusion current is going to get reduced and it's going to be almost zero. So the dominant current that's still here, because this electric field is there, is the drift current. So your total current will be approximately equal to your drift current, like that. And one thing that I forgot to mention is that this voltage source BR contributes to the barrier, so the total barrier is built-in voltage plus your reverse bias, and that's reflected on your formulas for width. So the width is increased by a factor of the square root of VR, and the same thing happens for the charge of the junction. So just as a summary for reverse bias, so when you apply a reverse bias, that means that the positive terminal of your voltage source is applied to the N side of the junction, the negative terminal is applied to the P side. You have an increase of the barrier, you have an increase of the width of the depletion region, which make harder for the majority carriers to diffuse from one side to the other. So your dominant current, or the main current that is acting when you have reverse voltage, is this IS, which is your drift current. So let's move on to forward bias. Here on forward bias, the opposite thing happens. So we are applying the positive terminal of the voltage source to the P side, the negative terminal to the N side. So we used to have an inherent electric field that was here under the depletion region, and now you're applying another electric field due to this voltage source that's on the opposite direction. So when you have this electric field, that's gonna subtract from your original barrier, so now your barrier is gonna be BO minus BF. So that gets reflected here on your junction as having a smaller junction, or having the width of your junction being less than it was before. So now you have a smaller junction here. I'm sorry. A smaller junction there. So how does that affect the current? So now let's look at the majority carriers again. You have these majority carriers here, holes on the P side, electrons on the N side. So now that they want to diffuse into the other side, they're facing a smaller barrier, so they're gonna diffuse easily to the other side. So you have an increase on diffusion current. This guy's moved from here to here. So the diffusion current is going to start being bigger than your drift current. So your total current will be diffusion current minus drift current. But since it is easier for these majority carriers to diffuse to the other side, this diffusion current is going to be dominant here. So you can also say that your total current is approximately equal to your diffusion current. And how is that reflected on the formulas from width and charge? We have them right here. So instead of adding the reverse bias voltage, you are subtracting the forward bias voltage. So you have a smaller width and we have less charge. So just as a review for forward bias, when you're applying the positive terminal of the voltage source to the P side, the negative terminal to the N side, you are creating an opposing electric field to the one that was already there due to the depletion region. So you're making it easier for your majority carriers to diffuse from one side to the other, therefore increasing your diffusion current. And this diffusion current is the one that's going to be dominant. So for a forward bias, your total current is almost equal to your diffusion current. And that takes me to the two review questions that I have from here. So what current is present at reverse bias? So at reverse bias, diffusion current is almost zero. So the current that is present is the drift current. And let's see, what current dominates at forward bias? So the current that dominates at forward bias, as I already told you, is the diffusion current due to the majority charges. The majority carriers, I'm sorry. So in the next video, which is going to be the last video from this chapter, we're going to talk about capacitances. Thank you.